Canadian scientists and engineers were pioneers in the field of vertical takeoff and landing aircraft. Their contributions would pave the way for future projects and excite the imaginations of millions. But perhaps none have captured imaginations more than the VZ-9 Avrocar, Canada's first attempt at VTOL flight. Preliminary design work for the Avrocar was started in 1952. It was unlike any other aircraft in the sky or under development. The Avrocar was a flying saucer powered by 3 turbojets. The unusual shape of the aircraft comes from the accommodation of previously untried aerodynamic principles. The concept began as a late 1940s study into new designs for engine compressors by influential Avro engineer Jack Frost. Frost decided to connect multiple engines together with a common compressor fan called a turborotor. This would allow the engines to work efficiently in all flight regimes and increase the overall thrust in a way similar to today's turbofan engines. In addition to this, he wanted to apply a newly emerging aerodynamic principle called the Coanda effect. It was thought that lift could be increased by sticking the exhaust airflow onto convex portions of the fuselage. The Coanda effect would cause the exhaust to be held against the surface by the ambient atmospheric pressure. This also draws ambient air into the airflow and increases the overall volume of thrust. This would, however, come at the expense of exhaust gas speed, but the benefits were seen to outweigh the cost. Frost and his team completed their initial engine design concepts in 1952, and then began looking for a suitable airframe. That same year, the Canadian government sponsored a contract of $400,000, allocated to the Avro company to begin work on the ambitious project, now called Project Y. The project would produce 2 separate designs to accommodate the new engine. The more successful of the 2 was a spade-shaped aircraft that landed and took off on its tail. Project Y was powered by a single turbojet engine that turned a large turborotor fan which surrounded the cockpit. The fan would draw in air from the 2 forward intakes. This acted as a compressor to the engine, but the majority of the air was ducted towards the leading edge through internal channels. Scalloped nozzles would direct the annular thrust rearward and lift the aircraft off the ground. A mock-up was created, but the complexity of the internal structure soon led designers to rethink the basic airframe. The more refined concept for Project Y2 was to create a circular wing, vertical takeoff and landing aircraft capable of high speed and high altitude flight. The flat riser would more fully take advantage of both Jack Frost's engine design as well as the Coanda effect. It used a series of turbojets whose exhaust was directed outwards towards the rim of the aircraft. The turborotor surrounding the cockpit was powered by the engines through mechanical linkages. It would draw in air through intakes located in the center of the airframe. The internal structure would redirect a portion of the accelerated air and duct it back towards the engine intakes. The rest would be directed downwards or towards the outer rim to provide thrust and control actions. Avro's development money ran out by 1954, and they were looking for other ways to fund the program. This is when the US Air Force took an interest in the Canadian project. They were trying to create a fleet of supersonic aircraft that didn't rely on highly vulnerable airfields in the case of an all-out war with the Soviet Union. The performance of the Y2 fitted this goal nicely, and so they allocated $1.9 million to further develop the concept. This interest motivated Avro to commit an additional $2.5 million of their operating budget to continuing the program. The funding allowed Avro to complete the design studies of many variations on the basic design. As the performance requirements evolved, the project was renamed PV-704 by its engineers at Avro, as well as Project 1794, Project Silverbug, and finally Weapons System 606A by the US Air Force. Paper studies of the various designs explored a wide range of capabilities from high-altitude supersonic flight to more attainable subsonic mid-altitude flight. Some scale test models were built for wind tunnel testing, and a few mock-ups of full-scale sections were produced. A full-scale engine setup of the PV-704 layout was also tested. Unfortunately, a series of fires and accidents caused the Avro engineers to lose confidence in the project, and testing was halted. In 1958, the US Army took an interest in the flat riser layout as part of their program to develop a flying Jeep. Although this concept didn't ultimately go into service, it did produce a number of interesting aircraft such as the Piasecki VZ-8 Air Jeep and the Hiller VZ-1 Pawnee. Later that year, the US Air Force agreed to transfer their part in the VZ-8 Air Jeep and the Hiller VZ-1 Pawnee. Later that year, the US Air Force agreed to transfer their part in the program to the Army in order to concentrate the effort and speed up development. It was intended that once the Army requirements were met, the concept could be developed back towards supersonic and high-altitude performance specifications originally set out by Avro and the United States Air Force. The resulting Army version was a much smaller vehicle than the 606A and was called the VZ-9 AV. Its designers at Avro affectionately named it the Avrocar. The aircraft was 5.5 meters in diameter and just under a meter thick. The Avrocar was powered by 3 Continental J69 turbojet engines, arranged around a centrally located 1.5 meter diameter fan. The performance expectations for the smaller 2,500 kilogram vehicle was a more modest 480 kilometers per hour at over 3,000 meters altitude. It had a predicted range of 210 kilometers with a 450 to 1,100 kilogram payload depending on the flight profile, all while being able to hover for 10 minutes in the ground effect zone. The outer surface of the aircraft is convex and is meant to provide lift while in forward flight, as well as cover the complicated internal structure. 2 cockpits are located opposite each other and embedded into the airframe. The exhaust thrust from the 3 engines powers the turbo rotor, which drew in air from the center of the airframe. Most of this was directed downwards, while a portion was ducted back into the intakes of the 3 engines. This had the effect of increasing the intake pressure in all flight regimes, resulting in greater engine performance. A portion of the engine's thrust would be channeled through the airframe to exhaust ports running along the outer rim of the disc. By adjusting the amount of thrust through the ports, directional control could be achieved. These adjustments resulted in asymmetric thrust, permitting in directional control. Unfortunately, it would also result in the aerodynamic instability, which would plague the system until its end. Two test vehicles were produced by Avro in 1957 and 1958. One was sent to NASA's Ames Research Facility in Moffett Field, California for wind tunnel testing, while the other remained in Toronto for flight testing. The Avrocar began tethered flight testing at the Avro plant on September 29, 1959. The pressure was on, as it had been just 7 months since the cancellation of Avro's other big project, the Arrow. Tests showed some instability while hovering and required a lot of pilot inputs to keep it steady. Pilots likened it to balancing a dinner plate on the tip of a pencil. The Avrocar was equipped with a gyroscopic stability aid which would assist pilots overcome this instability. However, it had little effect. Testing continued and pilots gained more experience with the tricky vehicle. By November 12th, Avro was confident enough with the design to begin testing the Avrocar in untethered flight. Test flights were carried out without the bubble canopy in the event that the pilots had to make a quick exit. At that time, the life-saving 0-0 ejection seat, enabling pilots to eject out of a stationary vehicle, had not yet been invented. The extensive testing revealed some major issues with the design. The Avrocar was found to only be operable in a narrow window of conditions. It could only achieve a maximum speed of 56 kilometers per hour and could not reach altitudes in excess of 1 meter above the surface. Wind tunnel testing confirmed that the design was highly unstable outside of that range and could not fulfill its intended flight parameters. A tail surface was added to try to increase stability, but the effort was unsuccessful. The design suffered from what Avro engineers called hubcapping. This is where the disc would oscillate around its pitch and roll axis. Pilots had a tough time keeping the aircraft pointed in the right direction, and so the control system was redesigned. Instead of using vanes to redirect air along the rim of the aircraft, a control ring was added to provide more continuous airflow and help reduce the instability of the lifting air column. Directional control was achieved by adjusting the magnitude and deflection of the ring, which resulted in the tilting of the exhaust gas relative to the body of the aircraft. Vertical lift was increased by moving the entire ring down relative to the airframe. This would direct more of the airflow downwards towards the ground and thus produce more lift. The gyroscopic stability aid was determined to provide insufficient assistance due to internal friction, and so a hydraulic boost system was added. Extensive refitting of the prototypes was undertaken to install the control ring, and testing of the design continued. There were noted improvements in stability and a reduction in the pilot's workload. However, despite the redesigns, the hubcapping effect remained largely unresolved. Unfortunately for the Avrocar's engineers, the problem was its basic design. The Avrocar was designed around a mostly untested aerodynamic theory that turned out to be much more difficult to master than previously thought. It couldn't maintain stable flight above the so-called ground effect zone, and this severely impacted its practicality as a combat aircraft. The Avrocar was demonstrated to the militaries of Canada and the United States, but its poor performance made any future development doubtful. The engineers and scientists at Avro took a risk with their design, but their application of new engineering and aerodynamic principles turned out to be a dead end. The Avrocar concept was finally cancelled in September of 1961. By then, a lot of money, talent, and time had been dedicated to the program, but all was not lost. Their work would go on to inform future Canadian projects in VTOL flight, like the more successful CL-84 Dynavert, built by Canadair. The Avrocar was a truly fascinating aircraft, and while some consider it to be a success, almost everyone would agree that the concept failed to live up to expectations.